All right, in this video, we're going to look at the type of correlation for the scatter plots that we create. So in our last video, we took a look at how to create a scatter plot, which if you're going to create them by hand, you might want to get some graph paper. Other than that, usually a lot of statistical software packages have the ability to create a scatter plot. Spreadsheet software does as well. Python is the one that I use for the scatter plots that I have to create. So you can do that using Python as well. So oftentimes the data in a scatter plot has some pattern to it. So in our one that we did in our last video, we saw that the data points have this pattern of somewhat going down as we go further to the right. So that would indicate that as time goes on, the value of the car tends to decrease, which is generally true for the vast majority of cars that are out there on the road. So a correlation between two variables examines how the response variable, or y, how that value changes as the explanatory variable, or x, as that value changes. So how does the y values of our scatter plot change as our x values change? What's the trend? What's the pattern to that to those data points? That's what we're looking at when we're looking at correlation. So we're going to examine three correlation types: positive correlation, negative correlation, and no correlation, or none. So first up, positive correlation, and that's where as x increases, so does the value of y. So here we have a scatter plot, just some generic scatter plot, but notice as we go to the right on our graph, means our x values are increasing, as we go to the right on our graph, notice our data points are going up in value. So we would say that this scatter plot has a positive correlation. And in our next section, we're going to take a lot more in-depth look at correlation. But for right now, we can get a general idea of the type of correlation by looking at the counts of observations in the quadrants formed by the means of our x coordinates and the means of our y coordinates. So looking at that last scatter plot, if we took all the x coordinates and found the mean of all of them, it's going to be roughly, looks like a little bit higher than 4. So we'll just say 4 to make it easy on ourselves. So the mean of all the x coordinates is 4. We can draw a vertical line at x equals 4. Likewise, if we calculate the means of all the y coordinates, we find that the means of the y coordinates is slightly higher than 12. So we'll just say 12 for the purposes of this video. And we can draw a horizontal line through y equals 12. So notice it creates a quadrant system: first quadrant, second quadrant, third quadrant, and fourth quadrant, just like in previous algebra classes. Well, we can get a general idea by counting how many observations are in each quadrant. So if we take a look at our first quadrant here, we have 5 data points in the first quadrant. In our third quadrant, which is our bottom left quadrant, we have 8 data points. So the total number of observations in the first and third quadrant is 13 values, 13 observations. Likewise, if we count how many are in the second quadrant, we have 2 in the second quadrant, and we have none in the fourth quadrant. So that total in the second and fourth quadrant is 2. So if we take a look at the difference in values here between the first and third compared to the second and fourth, there are 11 more points in the first and the third quadrant than in the second and fourth. So because we had many more points in the first and third quadrant, that's going to suggest a positive correlation, kind of like the slope of a line that is going through the first and third quadrant is going to be a positive slope. So that indicates that if it's a positive slope, that as x increases, so does y. Although we're not looking for any slopes just yet. We'll take a look at that in our next section. But in general, we tend to have a positive correlation when we have more points in the first and third, significantly more points in the first and third than in the second and fourth. So you can look at them as total percentages as well. 13 out of the 15 total points are in the first and third quadrant. So a very high percentage are in this first and third is going to indicate a positive correlation. Negative correlation is as x increases, the y values decrease. So here as we go to the right on our graph, our data points tend to start to decrease the further to the right that we go. Maybe they don't decrease very fast, but they have this downward trend to them, which is going to suggest a negative correlation. So if we look at the means of the x and y coordinates, we get about 4.5 for the mean of x, and maybe about I don't know, 10.5 or somewhere around there, a little bit less than 11 for the means of the y's. Counting the first and third quadrants, we have a total of 6 data points in the first and third. And in the second and fourth, we have a total of 9. So we have 3 more points in quadrants 2 and 4. 9 out of the 15 points are in the second and fourth quadrant. So it's going to suggest a weak or a very weak negative correlation when we have more points in the second and fourth than we do in the first and the third. And again, if we look at a line that has a negative slope, especially if we have the y-intercept at the origin, it's going to go through the second and fourth quadrant if the slope is negative. So again, there's that relationship between the value of r and the direction that the data points are going, whether it's positive or negative. Finally, no correlation. There's no visible pattern between x and y. So for all intents and purposes, you could take your grid here and just sneeze on your screen, and there you go. There's no correlation between where the particles land. So if we look at the means, here in the first and the third, we have a total of 7. In the second and fourth, we have a total of 8. Roughly half of them are in each of these two halves. So about half of the points in the first and the third, and the other half of the points in the second and the fourth. So there's not much of a difference, which is going to suggest almost no correlation whatsoever. In other words, as the value of x increases, you can't really predict what's happening with y. It doesn't look like it's going up, and also doesn't look like it's going down. So this is going to suggest almost no correlation between x and y in this particular data set. All right, so I wanted to end this video by discussing correlation versus causation because there is a difference between them. So it's important to note that just because there may be a strong correlation or an association between two variables, it does not mean that one causes the other to happen. With correlation, and this is going to be important in our next section as well, we're just looking for if there is an association between the two. It doesn't mean that one causes the other to happen or vice versa. And that's going to be very important to remember as we continue on with correlation and regression. So for instance, we could look at the association of a dog's paw size with the dog's weight. So typically, the bigger the dog's paw size, the more the dog's going to weigh. So we might notice that larger paws are going to tend to have larger weights, but we cannot conclude that large paws cause a large weight. So there's an association between the size of a dog's paws and the weight of the dog as an adult, but it doesn't mean that the paw size causes the dog to weigh more. There could be other things at play: genetics, breed, diet, exercise, that kind of thing. So we'll take a look at that in the next section as well. So if there is a strong correlation, though, between the larger paws and the larger weights, there may be lurking variables or confounding variables at play. So what a lurking variable is it's an explanatory variable that's not considered in a study or an experiment that has an influence on the response variable. So for instance, when looking at the paw size of a dog compared to the dog's weight, we might have lurking variables like diet. So if we have a dog that eats more, it might have smaller paws, but because it eats more, or perhaps doesn't eat as healthy, gets a lot of snacks and treats, it might weigh more than a dog with larger paws that is generally in better health. So a lurking variable is like it's lurking in the shadows. It has an influence on it, but it's not something that was considered in the study or the experiment. So if we're only considering paw size for the dog, there could be other things that affect the dog's weight besides the size of its paws. Confounding, on the other hand, is when we have too many variables going on at once, and we can't isolate the effects or distinguish the effects of one of them that it has on the response variable. So it's almost like there's too many cooks in the kitchen. So lurking variable is we don't consider it. Confounding is there's too much to consider, and we can't separate almost like separating the wheat from the chaff, so to speak. So, all right, that about does it for this video. Thanks for watching. I'll see you next time.